In this chapter 1.5, we're looking at applications of quadratic equations. Our first example and objective is to solve geometric problems. This is problem number 26 on page 155. The front face of a house is in the shape of a rectangle with a queen post roof truss above. The length of the rectangle is 3 times the height of the truss. The height of the rectangle is 2 feet more than the height of the truss. If the total area of the front face of the house is 336 square feet, determine the length and width of the rectangular region. So we first see our diagram, and that's the first step in our process. And so we're going to look at the diagram first, and we're going to break the diagram into 2 pieces. One is the roof part, which is the triangle, and the second part is the rectangle. We notice that the area of the triangle is 1/2 the base, which in this case is 3x, times the height of x. And the area of the rectangle is the width, which is 2x plus 2, times its length, which is 3x. Now we know that the total area is equal to 336 square feet. But that total area is made up of the triangle plus the rectangle. When we expand both expressions, we get 3/2 x squared plus 3x squared plus 6x. Now we combine the x squares, we get 336 is equal to 9/2 x squared plus 6. So we're going to divide both sides of the equation by 3/2. When we do that, we get 224 is equal to 3x squared plus 4x. And now we want to use the zero principle, so we have it in a quadratic formula. So we subtract 224 from both sides of the equation, and we see we get 0 is equal to 3x squared plus 4x minus 224. It turns out that this quadratic is factorable. It is factorable in 2 pieces, 3x plus 28 times x minus 8. Well, the only thing that works in this equation is the positive x, which is x is equal to 8 feet. So therefore, our area of the dimensions of the rectangle area is 24 feet in length and 10 feet in width. In this geometric problem, our objective is to solve it using the Pythagorean theorem. This is problem number 32 on page 156. The display area on a computer has a 15-inch diagonal. If the aspect of ratio of length to width is 1.6 to 1, determine the length and width of the display area. So again, we draw our picture, and we see that the hypotenuse is 15 inches. We have a right triangle, so we have the length and the width. And so the formula, the ratio formula, is length to width is equal to 1.6 to 1. And the other formula that we have is the Pythagorean theorem, which says that the hypotenuse squared is equal to the length squared plus its width squared. Well, now we know that the length is equal to 1.6 of the width, That's from our ratio. And from our quadratic, we will plug that length into where the length is. So 225 is equal to 1.6 w squared plus w squared. Now we get 225 is equal to 2.56 w squared plus w squared. We add the coefficients of the w squared, and we get 225 is equal to 3.56 w squared. And now we have the ratio 225 divided by 356 is equal to w squared, and we use the square root principle, and the square root of 63.202 such and such is equal to w, and we find that w is equal to approximately 7.95. We plug that in for length. 7.95 times 1.6 is equal to L, so the length is 12.72 inches. Our objective 3 is to solve quadratic models. So on page number 36, problem 36 on page 156, the gas mileage for a certain vehicle can be approximated by the following formula. M is equal to a negative 0.04 x squared plus 3.6x minus 49, where x is the speed of the vehicle in miles per hour. Determine the speeds at which the car gets 30 miles per gallon. And we have a hint, divide through by 0.04. So our first equation is what we set up based upon the information was provided. 30 is equal to a negative 0.04 x squared plus 3.6x minus 49. We're going to move the 49 over, so we get 79 is equal to a minus 0.04 x squared plus 3.6x. Our thinking here is that we're going to complete the square on this thing because it might be easier to deal with. So now we're going to divide both sides of the equation by negative 0.04. And in order for us to complete the square, we must get rid of the coefficient in front of the x squared. So when we do that, we get a negative 1975 is equal to x squared minus 90x. Now we take half of 90 and we square it and we add it to both sides of the equation. And in this case it's 2025 to both sides of the equation. We see that when it's subtracted from this side of the equation we get 50. And when it's added and we have a perfect square, we just have x minus 45 squared on the right side. And now we use the square root principle, and we get plus or minus the square root of 50 is equal to x minus 45. Well, we see that we can reduce the square root of 50 to plus or minus 5 square root of 2 is equal to x minus 45. And so we add 45 to both sides of the equation. We get x is equal to 45 plus or minus 5 square root of 2. So our estimates for getting 30 miles per gallon, I can either travel at 52.07 miles per hour or I can travel at 37.93 miles per hour. The last objective, objective 4, is to solve quadratic motion problems. So we're going back to skill practice number 5, page 154, and we're going to make some modifications to this problem, which we find very interesting. So it says a firework mortar is launched straight upwards from a pool deck 2 meters off the ground at an initial velocity of 40 meters per second. It says write a model to express the height of of the mortar in meters above the ground. And we note that in this case, since it's in metric form, we have that gravity is equal to 9.8 meters per second. So the formula for distance in relationship to velocity and acceleration is the following. S is equal to 1/2 g t squared plus v naught t plus s naught. We can translate that directly by just plugging in the information from the problem, and we see it's S is equal to 1/2 times 9.8 t squared plus 40t plus 2. And our final result, when we multiply the negative 1/2 by 9.8, we get a negative 4.9 t squared plus 40t plus 2. We're going to use this equation throughout B, C, and D. So in B it says find the times at which the height is 60 meters. So we plug in 60 into S, and then we of course use the zero principle to set it equal to 0, and then use the quadratic formula. As you can see from the quadratic formula, t is equal to a minus 40 plus or minus the square root of 1600, which is the square of 40, minus 1136.8 divided by 2 times a negative 4.9. And so our estimate for t at heights at 60 meters is at 1.9 seconds and at t at 6.3 seconds. Our second problem is not in the book, but I think it's important because we will be solving these problems later down the road. It says find the maximum height that the mortar reaches. There's a formula for that, and I'm going to give it to you now. It's t is equal to a negative b over 2a under the quadratic form. So in this case, remember, under the quadratic formula, b is equal to 40, and a is equal to a negative 4.9. We plug that into the equation, and we get a negative 40 divided by 2 times a negative 4.9, and we end up with 4.8 seconds. So at 4.8 seconds, we're at the maximum height of the firework mortar. Now, in order to find the height, we have to plug it into the original equation for S, and when we do that, we get an answer of 83.63 feet. Finally, the last question says, how long is the mortar in the air? Well, when the mortar gets to the ground, guess what? S is at 0, right? So we set the equation to 0. So 0 is equal to negative 4.9 t squared plus 40t plus 2. When we put that into the quadratic equation, right, we get t is equal to 8.3 seconds. So the firework mortar that's launched takes 8.32 seconds to completely hit the ground after it's gone up in the air. So there's our problem for motion problems. Please review these problems, and we'll discuss any issues on our problem set of the day problems.